Welcome to Motion Graphing Part 2, where we're going to talk about moving between graphs. So the question is, how do we move between a position graph, a velocity graph, and an acceleration versus time graph? An important thing to know is that the slope on our position graph is equal to the velocity at that moment. So if we look at this position graph and we look at the slopes, those are going to be the velocities. So we can look at slopes at different places along the graph, and we can see that the slopes are positive but getting bigger. At the beginning, the slope is almost zero, and it increases as we go up. So because of this, we know our velocity is going to start at zero and increase just like the slopes. So when we are able to determine the slopes on a position graph, we can figure out the exact direction of our velocity graph. Next, the slope on our velocity graph is equal to our acceleration. So it's the same thing except position to velocity. We now are doing velocity to acceleration. So if we look at the same graph, we can see that it has a constant slope, and that's our acceleration. Remember, when you're looking for slope, that we're always using rise over run, which is why a steeper line has a larger slope, because there's more rise. So because of that positive slope we just saw, we know we have a positive acceleration. We'll always be dealing with constant acceleration, so all we really need to worry about is whether it's above the x-axis, on the x-axis, or below the x-axis. But let's look at some patterns that will help. So there are two basic patterns when we move between position, velocity, and acceleration. Either way, you're still going to need to look at the slopes to get the exact sketch. So the first pattern takes us through curved position graphs. Here's an example of a curved position graph. What we're going to do is we're going to look at the slopes, but we will always get a velocity that is a straight line but isn't horizontal. So here are some examples of what it could look like. But we don't actually know which one is right until we look at the slopes. When we look back at our position graph, we can see that we have a large positive slope, a medium positive slope, and a near zero positive slope. So our slopes are positive but decreasing. This tells us that our velocity must also be positive but decreasing to zero. So we're able to graph this. We see that we had a positive velocity that is getting smaller and smaller as it approaches zero as time goes on. When we want to move to acceleration, we follow the same steps. Since acceleration is going to be horizontal, we just need to decide if velocity has a slope that is positive or negative. Using rise over run, we can tell that this velocity graph has a negative slope, so our acceleration will also be negative. The second pattern we're going to look at is for straight position graphs. Here's an example of a straight position graph. You'll notice it can be anywhere, but it won't be curved. In this case, we're always going to get a velocity that is a horizontal line. But again, we don't know what it looks like without using slopes. So we go back to our position graph, and we notice that we have a positive slope on our position graph. This means that our velocity will be a constant positive value. So we can go back and pick a reasonable value. If we have no change in velocity, which is what this graph shows us, there's no change in velocity, we can see that acceleration will be zero because our velocity graph had no slope. So as an overview, there are two main patterns. A curved position graph leads to a straight but not horizontal velocity graph, which leads to a horizontal but not zero acceleration graph. A straight position graph leads to a horizontal velocity graph and a zero acceleration graph. But no matter what you do, when you're solving a problem and making sketches, you must check the slopes.